Hello, my name is Dylan Hacker, and today I will be explaining the variation of temperature and pressure as we increase in altitude. To start off, I would like to write down 4 basic equations that we will be using today. The first equation will be the ideal gas law, PV equals nRT. Pressure times volume equals moles times gas constant times temperature. For our second, we will be using the basic law of statics, which states the change in pressure over the change in altitude equals negative rho density times gravity. For our third equation, we will be using Cp, which is the heat capacity at constant pressure, equals R gas constant plus heat capacity at constant volume. And along with this, we'll be using the ratio of K, which equals Cp over Cv. And for our fourth equation, we will be using the first law of thermodynamics, which is du equals dq minus the external pressure times delta V. And starting off with these, we will also be using some assumptions. The first assumption is that we will be using 1 mole of gas, or air, I should say. And our second assumption will be that the atmosphere is isentropic. And this means that it is both adiabatic and reversible. Alrighty, and what that means is as the pocket of air travels up into the atmosphere, it expands gradually so that the external pressure and the internal pressure are both equal and there is no transfer of heat. So moving to the last equation, the P external will just be P and there will be no Q. So the change in heat will be 0. So that is what it comes to. And with the 1 mole of gas, we get pressure times volume equals RT. Alrighty, now starting off, we will be dealing with the second equation right there. And we want this in terms of P and T. So using the ideal gas law, we will be substituting out density and substituting in pressure and temperature. So what we get is the change in pressure over the change in altitude equals the negative molar mass times pressure, which is big M and P, keeping gravity in there, over RT. Now we're going to move the T and the P onto the left-hand side, and we're going to move that delta Z onto the right side. So we get T over P dP is equal to the negative mg over R dz. We will be coming back to this equation in just a moment. First, we have to get this equation right here in terms of T and V so that we can differentiate it, because du is equivalent to the heat capacity at constant volume times the change in temperature. So we get Cv dt equals negative, and we want to substitute volume and temperature in there using our ideal gas law, getting pressure out of there for now. So coming back, we get RT over V dV, and that is still negative. And now we have to put the T on the left side so that we will be able to do a simple separable differential equation. And it is going to be from T1 to T2, V1 to V2. Now this is just a simple differentiation, leaving us with the natural log. So keeping the CV out in front, we get CV times the natural log of T2 over T1. And that's going to be equal to the negative R times the natural log of V2 over V1. And now, using some laws of natural logs, we can put the negative R over CV. We'll move that on up to the exponent on the right-hand side, leaving us with the natural log of T2 over T1 is equivalent to the natural log of V2 over V1 raised to the negative R over CV. And once we have this, we can just exponential both sides, put the E in there, boom, get that out of the way. T2 over T1 equals V2 over V1 raised to the negative R over CV. Now we don't want volume in there anymore because we're trying to find the relationship between pressure and temperature. So we need to use the ideal gas law once again to get volume out of there and then pressure in there this time. So back to this, we will be separating that. And from now on, I don't want to be using 2 as the final. We're going to be leaving that as T and P. And now once we have that right there, where the R's do cancel out, and this part also equals TP1 over T1 times P. Still raised to the negative R over CD. Now once we get that right there, we want to go ahead and move the T over T1 onto the left-hand side. This will give us to the power of 1 plus R over CV equals, we want the P to be on top of the P1 to get rid of that negative exponent. And going back to the K value right there, we're going to be plugging K in to both of these. T over T1 raised to the exponent of K equals P over P1 raised to the K minus 1. Right, like that. And now we want to go ahead and separate that T to get T as a function of P. And to do that, we need to raise both sides to the 1 over K. And that'll give us T times T1, or equals T1 times P over P1 to the K minus 1 over K. And once we have that, we can go ahead and get ready to substitute this back into the equation we solved beforehand. This one right there. So we go ahead and we get the integral T1 times P over P1 raised to the K minus 1 over K over P dP equals negative M G dZ over R. And the one on the right is a very simple integration, as we just end up with delta Z, the change in Z, Z final minus Z initial. And the one on the left-hand side, we're going to take out the constants to make it a little bit easier for ourselves. So we get T1 times P1, we want that P1 to be on top, so we go ahead and do 1 minus K over K. And this is going to be to the P, so from P1 to P2. And the exponent on this one is going to be K minus 1 over K, and then we're going to bring that bottom P all the way up to the top, and that's just going to add a minus 1 onto it. And now what we want to do is we want to move this stuff on the left-hand side onto the right-hand side, those two constants, so we leave the integration all by itself. And we want to keep that P1 as a numerator. Ooh. And then we're left with that right there. And then once we go ahead and do that, we can do the integration on the left-hand side. So we get P1. First, we have to start out with adding 1 and then doing the reciprocal. That times P2 to the K minus 1 over K minus P1 to the K minus 1 over K. And already we recognize that this right there and that right there are both the same, so we're going to go ahead and move that onto the right hand side along with our constant out in front. So once we do that, we get P2 left by itself. Save that for later. We get that times 1 minus K minus 1 over K, and then the molar mass times gravity times delta Z over RT1, right, like that. And now this is an exponent right here. That was not clear. Let me fix that up right there. There we go. And now we want to go ahead and take the reciprocal of this, K over K minus 1, right, like that. And then move that on to the right-hand side as well. So once we go ahead and do that right there, we are left with P2 by itself. P2 equals P1, our initial pressure, times 1 minus K minus 1 over K times the molar mass times gravity times the change in altitude over RT1. And that inside the parentheses right there is all going to be raised to the power of K over K minus 1. And there is the equation which relates the final pressure, assuming you the nodes of change in altitude as well as initial pressure and initial temperature. But we want to get the equation for final temperature as well. And in order to do that, we just plug this equation back into this equation right here. So we get T equals T1 times, and that P is on top, so P1 times 1 minus K minus 1 over K mg, this parentheses, delta Z over RT1 over P1. This is raised to the K minus 1, or K over K minus 1. And this right here is raised to the K minus 1 over K. So the P1s cancel out. These two exponents cancel out. And you're left with T equals T1 times 1 minus K minus 1 over K molar mass times gravity delta Z over R T1. Exactly like that. Those two equations right here, this one and this one, are the two that we were looking to find to relate pressure and temperature as we increase in altitude. Thank you so much for watching. I hope you guys enjoy the rest of your day.